Physics Learner Space live session. So this is a small introduction to this is a small introduction. You can see the presentation perfectly, right? Just give me a yes. Someone, please. Okay. Um, Yashvi, just confirm whether you're able to see my screen. Yes. Okay. Uh, I shall be starting now. Okay. So let's see. So the contents that you are going to find in the module, which I shall be trying to give a brief introduction of, so and to pique some interest, are the following. You will be studying the solar structure. So we'll be learning about what the solar dynamo is, what a very important effect of astronomy called the limb darkening effect is, and a very important phenomenon present in the sun is the differential rotation of the sun. We shall be studying about that, and you'll also be given references and further reading so that you can go above and beyond, because solar physics is genuinely a very vast topic, and it has extremely complicated physics and mathematics behind it. So the references and the reading materials to be covered are pretty much endless. So the sun, yes, we see the sun in the sky. It is extremely bright. It literally lights up the entirety of the earth while it is in the sky, obscures us from seeing anything else. It is humongous, at a even at a distance of 1.5 into 10 to the power 11 meters. It appears to us as big as the moon. So one could easily understand that it's huge. Its volume is equivalent to that of 1.3 million Earths in front of the sun, yet it only appears as a ball, a small ball in the sky. Its temperature is 15 million degrees Celsius at the core. Reminder that this is the temperature at the core. The actual the temperature of the surface is way lower than this. It's nearly 5,000 Kelvin. This is the temperature at the core. So the sun is an essential power source for running practically everything on the earth. Solar energy, wind energy, even like even hydel energy, all the energies are, except nuclear energy, are essentially derived from solar energy. And given that it spews, and given that we receive only a small amount of the energy the sun spews forth, it is obvious that the sun actually emits a huge amount of energy. But the question is where all of this energy comes from, um, and how it is sustained at such a low temperature. Okay, wait. I'll come to the latter point later, as to even why I'm calling it a low temperature. The power source of all this energy is fusion, as you guys would already know. Nuclear fusion. Hydrogen fuses to form helium and other heavier elements, and which is what releases the energy that comes to us through the sun. Uh, why I say that it is a relatively low temperature for fusion is because fusion usually happens at like fusion achieved on Earth in artificial conditions has been achieved at temperatures of billions of Kelvin. And here we're talking about millions of Kelvin. So the difference actually comes from the fact that by the sheer amount of molecules in the sun, the sheer number and sheer closeness, the even a very small probability of them fusing leads to a decent amount of fusions happening. So even at such a low temperature, a decent rate of fusion is maintained in the sun. Uh, Now, if you look up into the sky and stare directly at the sun, which is not at all advised, you will burn your retinas. Uh, you will get the illusion that the surface of the sun is uniform, but it is not the case. If looked at with the proper tools, the sun's surface is actually pretty non-uniform, as we will see in this presentation. But the physics of it is, and we'll also look briefly into the physics of why the surface of the sun is in fact non-uniform and how it comes about. Just to give you a small introduction of what natural phenomena, what natural phenomena can be understood by understanding solar physics, we have included this slide. As you can see, uh, in the lower image, solar physics is auroras are a direct consequence of what goes on in the solar atmosphere and beneath it. Uh, the part, the the it's like auroras are created by the particles released by the sun when they interact with the Earth's atmosphere. Another interesting effect of solar physics is the fact that the heliosphere, which is the volume of influence of the sun, actually actually is a very important um, actually is a very important thing for us, because it shields the solar system as a whole from harmful radiations from the outside, and that's another direct consequence of the physics of the sun. So as you can see, these are two very cool effects. One very cool to the eye, and one pretty necessary for our livelihoods. Let us start by talking about solar structure. So, as you can see, the sun has many layers. The outermost layer is the corona. The and as you can see, as we go inside, we come across the photosphere. So, first of all, let's talk about the corona. The corona is essentially what what we find beyond the visible surface of the sun. It is filled with extremely hot plasma, reaching temperatures of near about 1 million Kelvin. Now, this will sound contradictory given the fact that the surface of the sun is at a very low temperature, and I'm saying that corona, in fact, are at temperatures of millions of Kelvin. Now, this is a very interesting apparent contradiction that can be explained by solar physics as well. And as you can find in the as you can find in the module, the discovery of the high temperature of corona, in fact, is in itself a very interesting thing to study. Uh, and yes, that's that for the corona. Now we shall for the visible layers of the sun, we are going to go from the inside. Let's talk about the core. Core is obviously where all the nuclear reactions of the sun take place, which is the source of its energy, and it is basically where all the high energy photons are produced. Now these are converted to the visible spectrum and lower and higher energy as it travels to the outside, but inherently inside, extremely high energy photons are released. Um, Beyond the core, we have the radiative zone. The radiative zone is the layer of the sun where energy transfer takes place through radiation. Uh, yes, so convection does not have much of a role during this time, because like the temperature gradient uh, and the capacity to flow to facilitate convection during in this layer. Essentially, this is a very hot photon bath where the entirety of the energy transfer takes place through radiation, and it is the thickest layer, as can be seen in the slide. It extends to a humongous radius of 0.45 solar radii. One interesting fact, uh, the photons that are reaching us now, the origin of them was like takes millions of years. Takes, okay, wait, let me find the exact number. Uh, yes, it takes to the order of millions of years for a photon released in the core of the sun to actually reach the surface. Why? Uh, why? Because a photon gets absorbed by another particle, which again re-emits it, which again is absorbed by another particle. If the follows an extremely zigzag path, and which is exactly the reason that the photons that reach us represent the black body spectrum of the particles on the outer layer rather than the high energy photons that are released inside, because the photons keep getting processed by absorption and re-emission again and again and again, which is also the reason it takes a photon released from the core to so much to us. So yes, beyond the radiative zone, there is another layer. There is a transition layer in like mainly takes place from uh, where energy transfer takes place to convection. Between them, we find another layer called the tachocline, which is essentially it's between both of them, partially both of the hi, I am back. Where did you guys lose me? Harsh, Kriti, if you can just tell me. Um, okay, assuming you guys didn't miss much, I'll just continue from where I was. Um, yes. So, okay. Wait, I am sorry. I think there's a network problem. Let me try to fix it. Hi. Um, Harsh, can you hear me? Can you just confirm whether I'm audible? Okay, I am audible. Okay, thank you. So I shall let me just rejoin the meeting. Okay, hi. So and apparently, like on solar scales, this is cool enough for the heavier ions such as carbon, nitrogen, oxygen, calcium, and iron to hold on to some of their electrons. Before this, at high enough temperatures, none of the atoms actually can hold on to their electrons. So it's all all nuclei and their electrons roaming around essentially. Now we are going to be talking about an uh, extremely important phenomenon observed in astronomy, and this is something that actually helps us analyze transits as well. So limb darkening is an effect that is observed in a lot of luminous bodies. First of all, suppose limb darkening wasn't there. Suppose if I was looking at the sun and it appeared uniformly bright to me, the disk was uniformly bright, I would say that the surface of the sun is a Lambertian surface. What is a Lambertian surface? A Lambertian surface is basically, imagine a disk with some luminance, some brightness. If you look at it from different angles, if the apparent brightness per area does not change, if the apparent brightness per area does not change, regardless of where you look, where you, regardless of what orientation you look at it, then it is called a Lambertian surface. And and then the amount of energy it releases in a particular direction is actually proportional to the cosine of the angle made by your line of sight to the normal, and hence it's called the Lambertian cosine rule. Point is that uh, if the surface of the sun was to be a Lambertian surface, the entirety of the at an angle, and the brightness per area should not have changed. Uh, the surface of the sun is not a Lambertian surface because there are a lot of intrinsic effects going on, and you will find details of it in the module. But essentially, there is some preference in releasing energy normal to the surface. It is lesser photons go in other directions, and the normal assumptions which makes us assume that a lot of surface are Lambertian surfaces does not hold. If you were to observe the sun using sufficient filter so that you do not get burned, you will see an image like the image on the right. As to why there are black spots, those are called sunspots, and we will be learning about them later. But you can see there's a gradient as we go from center to the right. So let us think about this question. Does all of the sun rotate about its natural axis with the same angular velocity? This does seem intuitive because the earth indeed does, all of the earth rotates about its own axis with the same angular velocity, and one wouldn't assume that the sun should be anything different, but as a matter of fact, uh, it is not the case. The angular velocity varies with depth from the surface of the sun, and it also varies with latitude. This can happen because the sun is not a rigid body like the earth is. We already know that convection itself takes place in the sun, so it's not a stretch to assume that the sun is not a rigid body and different parts of it rotate with different angular velocities. Uh, so as a matter of fact, this gives rise to a lot of interesting physical phenomena. Obviously, given that the layers are moving at an apparent angular velocity with respect to each other, they do experience shear force, which causes interesting things, and which are kind of beyond the scope of this. But one another interesting thing regarding the differential rotation of the sun is that it is believed that the dynamo effect, which we will learn about later, has has a huge, like the cause of the dynamo effect is hugely attributed to the differential rotation of the sun. Understanding the sun's differential rotation, which you will take another step towards while reading the module, is a very important step towards understanding solar physics. So now to the $1 million question: why are there spots on the sun? If there are indeed, if the sun is a ball of huge fire, fire just doesn't go dark at some places. It doesn't make sense. So starting off, sunspots are features caused by the magnetic field of the sun. The magnetism of the sun is a huge physical effect which causes much of the phenomena that we see. As a matter of fact, the heliosphere that I talked about in the first slide, was the first or the second slide, is also a consequence of the magnetic field of the sun. Uh, the magnetic field of the sun is explained by the solar dynamo theory, which I just mentioned in the last slide. Uh, the we have You have interesting visuals um, in the module that partially tell you how it works. So we know that charged particles like revolving do cause magnetic field, and there are effects which take place in the sun, which cause, partly attributed to the differential rotation of the sun, which cause the charged particles to go around in circles, and which you can, as a matter of fact, read more in the module, which causes the magnetic field. Uh, Another interesting thing about this is the magnetic field of the sun goes through a cycle that lasts nearly 11 years. This is popularly known as the solar cycle, and the like the peak and the valleys of the sun are, as a matter of fact, noticeable in our day-to-day lives as well, because during peak solar activities, sometimes solar storms are released, which have caused power outages in on Earth. So, to give you a brief idea of how sunspots are formed on the surface of the sun, at certain points on the sun's surface, the amplified magnetic fields, there are particular parts on the sun's surface, where the magnetic field gets stronger, and they become buoyant and break through the surface. So they hinder photon release from that part. Either they like that the region of the sunspot is usually colder than other regions, which is why it is not nearly as luminous as well, which is why you which is why these appear as spots when we try to photograph the sun. So that is all. To go I would encourage you guys to go through the module on Kritika's website for more information. Uh, if there is any question, it is most welcome now. Is there anything I haven't addressed? I don't think so. Yes. Any questions? Okay. Um, so I think